Alright, in this section we're going to talk about the graphs of logarithmic functions. And what we know is that parent logarithmic functions look like y equals log base b of x. For any base, b is greater than 0, b cannot equal 1. Remember, these are the rules for the base of the logarithm. It must be a positive number and it cannot equal 1. Remember, these are the same exact rules that we had for the base of exponentials. Remember, the base of an exponential, when we wrote it, could not be equal to, if we had f of x is equal to b to the x power, the b here must be positive and it must not be equal to 1. So it not only has to be positive, but it has to be non-zero. So it has to be greater than 0 and it has to not equal 1. If it does, the thing is, it still exists, and even if it's b is negative, it exists. The thing is, it's not going to behave like all the other exponential functions. And that's what we're looking for. We're looking for something that has consistency to it. And when we put these limits on the base of the exponential and the base on the logarithm, they have very consistent properties that we can use. If we get outside of these, then they're not as consistent and those properties do not always apply. So that's why you've got those limitations. All right, so two key points are always going to be on your parent log graph. Now remember, when we say parent, we're talking about it's not going to be stretched vertically or horizontally, and it's not going to be shifted up or down, left or right. This is the base graph that we do before we do those transformations. The two key points that are there are going to be 1 and 0. That's going to be the x-intercept. And hopefully you can see that log base b of 1, anything raised to the power of 0 equals 1. That's where that point comes from. It's going to be true no matter what b is. The second point that's always going to be there is the point b1. And what's going to happen there is if we take the log base b of b, remember we're asking with a log, what power do I raise this base to get that? And that's where it's going to be equal to 1. So those points are always going to be there. So here's that one and here's that one. And those 2 points are going to give us the general idea of what kind of a graph we're going to have that we're looking at. Now, we also have a vertical asymptote at x equals 0. We have a vertical asymptote at x equals 0 because of this thing right here. And that is why we would have a vertical asymptote right there. So that vertical asymptote means we cannot cross it. We're not going to have values over here. Once again, remember, with the parent or the base log function. We can do other things to reflect and all kinds of stuff like that, but the base log is not going to be over in the negative. You're going to be in quadrants 1 and 4. And it's going to approach that vertical asymptote this direction, and it's going to grow off to infinity in this direction. So that's where we get the domain being x is greater than 0, and the range is all real numbers. Now the vertical asymptote here, once again, the reason why it is only positive numbers is because we can only put positive numbers in here. Just as a for instance, let's say we had the log base 2 of negative 8. Is there any power that you can raise to get a negative number of any kind? Not even just negative 8, but any negative number. No, there's not. So it doesn't exist. So we cannot take the log of a negative number. So what's inside of that log must end up being positive before we take the log. We're going to see that here in just a second in an example. And b of x and log base b of x are inverses. They undo one another. We can see that right here with the purple line. That is, if you remember, that is the exponential function. And in this case, it's the function b of x, or b to the x power. And you'll notice that this point and this point, this point and this point, they both exist on both of them. And what do we notice? The x and the y just change positions, as we should expect with every single logarithm, and every single inverse that we deal with. Now, not only that, but this thing, the entire graph, is going to reflect across that line, and that line is y equals x. And that gives us yet another thing to remind us what happens with every single point as we move from the point of the original function to the point of its inverse. Y equals x, x equals y. So you swap them. All right, now, the fact that these are inverses includes all base logs, all based exponentials. So this includes e to the x and log base e to the x, which is, of course, ln x. These two are inverses of each other as well. All right, so for number one, we're going to graph f of x equals log base 3 of negative x without a calculator, and identify the following. What's the vertical asymptote? What's the x-intercept? What's the domain? And what's the range? All right, now some of you are probably freaking out already and saying, well, wait a minute, you just said we can't take the log of a negative number. That's still true. We cannot take the log of a negative number. So what has to happen is this thing right here must end up being a positive number for a valid y value to come out of it. So if I went over here and I chose 1, let's choose the number 1. If I plug it in here, I'm going to end up with log base 3 of negative 1 when I multiply by that negative, and I cannot find its value. It doesn't exist. D, N, E. But what happens when I take negative 1 and plug it in? Remember, I've got the negative, and then if I plug in a negative 1, my negative times negative gives me a positive. So now I have a log base 3 of positive 1, which gives me 0. So at negative 1, I have the point 0. So if you think back to our transformations and flips and reflections and all that, what happened when we went from f of x to f of negative x? What did it do? Well, it took everything that was over on this side that was happening when x was positive, and now it makes it happen over here where x is negative. And if you had stuff over here where x is negative, it now moved that over here to where x is positive, because that right there changes the sign of the x. Whatever number you put in is now the matching one on the other side. If you put negative 1 in, it's now matching the one on the other side of a positive. So that is what we're running into. So we have a reflection. This gives us a reflection, and it gives us a reflection across the line, the x-axis, the y-axis, or the line x equals 0. Now that just happens to be our vertical asymptote. So our vertical asymptote is x equals 0. So let's go ahead and draw that in. Now you do not have to draw those axes in. I'm going to do a little better job with that. Hold on just a second. That way we can see it just a little bit better. And I'll move it over. All right, so there's my vertical asymptote. And remember, we're not going to cross it, and we already have one point that's right here. And then our x-intercept is going to be at -1, 0. And then if we put in log base 3, if we were to go in and put in 3 again, we end up with the negative x value, so that would be -3, which does not exist. But once again, the same exact way we did with the -1, if we flip over to the other side and do -3, log base 3 of negative, that's this one, and then plug in the value -3, we end up getting the log base 3 of negative times negative gives me a +3, and that's going to give me 1. So over here at -3, because that's the value that I plugged in for x, I'm going to have a value of 1. All right, so hopefully you can see now that this is just a reflection across that y-axis. So our graph is going to approach infinity as we go in this direction. It's going to get closer and closer. I know I can't draw, but it's going to get closer and closer and closer to that horizontal or vertical asymptote. And then as we go up this direction, it's going to go off this way. So there is our graph. That's going to be our graph of y equals log base 3 of -x. So what is the domain? Well, the domain, remember, are all the x values that you can plug in and get valid y values out. So that's going to start way over here at -infinity. And it's going to increase and go all the way up to 0, but it does not equal 0. Because if it hits that vertical asymptote, you're going to get issues. So you can't take the, and the reason we've got that vertical asymptote is this. Think about this. If we have log base 3 of 0, what power can you raise 3 to get 0? Well, there's not one. And once again, it's a does not exist. And then the range, well, the lowest y value that it can have is -infinity. And the greatest value it can have is +infinity. Now keep in mind, this thing's going to keep going off over here. It's going to grow at a slower and slower rate, but it's still going to keep growing. It's going to grow as long as you keep plugging values in. So that function is going to go over here and get infinite as well. It's just going to get there a lot slower than this one's going to on the right side. All right, number 2, we're going to match the following equations with their graphs, and we're not going to use a calculator. In other words, you should be able to look at this and determine what kind of transformations are happening and which one is the one that it's going to look like. So I'm going to go ahead and give you a little hint here as you're going. Remember, if we do a negative out front that we're multiplying by, ignore the 2, just the negative. Remember, that's going to flip things from above the x-axis to below the x-axis and below the x-axis to above the x-axis. So it's going to reflect across the x-axis. So the ones that are going to have negative out in front of them are going to flip over from what we're used to. In other words, this is a negative. This is a negative. All the other ones have positive numbers in front. Can you guys see that? This is your general shape of a log graph. This is flipped over. This is flipped over. So those are the two that are going to be negative in front. So right there you can limit yourself down, and you've got one over here and one over here. One that has no shift whatsoever, it just has the -2, and one that has a shift up of 2. So now which one of these two graphs is higher? And what we're going to do is we're going to go up here, and we're going to label that one 1, and that one 2, and that one 3, and that one 4, and that one 5. And then we'll go down here and we'll put the correct equation number next to each one of the graphs. So is this one shifted up 5 or is this one shifted up 5? Well, that one's obviously shifted up 5. Because if you just take that point right there, it's up higher over here. So that means that this is going to be number 4. And if that's number 4, then this one over here has to be number 1. All right, so we've dealt with that one. We've dealt with that one. Now let's look at the other ones. Well, the other ones, the first big thing that should jump out at you is one's got a 3 and the other two have 1/2 in front of the log expression. We'll look at the shifts later. What does the 3 do? Well, you need to think about it like this. Think about log base 2 of x. Think about this being your original y value. And if we take and we multiply 3 times all those original y values, sorry, let me change that to a plural, values, what's going to happen to every single value? It's going to be 3 times as much as it was before. So that means we're going to do what? We're going to go up at a faster rate because now our y values are 3 times what they were before. So now as we look at what we got left, that one doesn't grow very fast. That one doesn't grow very fast. This one grows really fast. So I'm going to go with that being 2, simply because it's growing at a much faster rate than these other two. Because the y values on the positive up on above the x-axis are 3 times what they were with the other ones. Now keep in mind these other two are both going to be 1/2 of what they would have been. Notice we don't have a base graph here. We're just breaking down and seeing which ones are which. So now the cool thing about these two is they both have 1/2, so they're going to look the same. But what's going to happen when we put the -5 inside here and the -5 outside the log function here? Well, remember, this is going to be 5 units down because anything outside is going to go the direction of the sign and exactly the number that we're going to go. Inside, remember, it's going to be opposite the sign. So if -5 would indicate left, this is actually going to go right 5 units. So now just break down which one's which. Which one went down unit? This one right here. So E is 5. This one, oh, nope, hold on. This one shifted over, including that vertical asymptote. That vertical asymptote is now over here at +5. So A is going to be 3. So break down, first of all, break down and see if there's any negatives, because those are going to jump out. They're going to be flipped over. They're going to jump out and be very different from the other ones, unless they're all negatives. And then just break down and look at what you're multiplying by. Is it growing faster? Is it growing slower? Notice these are growing much slower. They don't look like a basic log graph. And then you can look at your shifts to narrow it down even further. All right, number 3, we're going to write an equation for a logarithmic function that has a vertical asymptote at x equals 5 and goes through the point 11, 1. All right, so we're going to start off with writing our equation. Y equals log base b, we don't know what the base is, of x, but we also know we have a vertical asymptote at x equals 5. Well, just like that last one we were looking at there, that means that we're going to shift this whole thing to the right 5, which means that inside the function we're going to subtract 5. So that's going to be the values that we have. Now, we have an x and y right here. We can plug those in. So 1 equals log base b of 11 minus 5. 1 equals log base b of 6. Now, what log, if b raised to the first power gives me 6, what does b have to be? Well, b must equal 6. Now, if that causes you some problems, remember, you can always take any log, anytime, anywhere. You can rewrite that thing, as long as it doesn't have crazy stuff attached to it, you can rewrite that thing as an exponential. Log base b of 6 equals 1 can be rewritten as b to the first power, because remember the answer to a log is the power, equals 6. This is the value that the exponential is going to equal. Now, what would I have to raise to the first power to get 6? Well, I would have to raise 6 to the first power to get 6. So now when I put everything together, my equation is y equals log base 6 of x minus 5. That is going to give me a logarithmic function that has a vertical asymptote at x equals 5 and passes through the point 11, 1. All right, hope that helped a little bit.